Hi, everyone. Good morning, good evening, and good afternoon. Really excited for this, specific webinar about the state of AI in the mining industry. This is would be a very fun topic to discuss. There is no technical specificity. We will go into the details, but consider this. This is like what we have been developing or doing as an industry, and also more kind of relevant to the Strayos over the last kind of several years, how far the industry has come along in the adoption of the AI, and then also where it's going, where it's moving. That's been the key focus for today's discussion. We will really go into the examples, what has worked and what has failed, and what was the lessons learning that came along throughout that process there. So let's dive in here. So let's start with what is the opportunity and what was kind of the mining industry feeling the pressure here, right? So when we talk about the estate, like we gotta go back and like really understand why this matters, right? And why the AI matters in the mining industry, because the demand for critical minerals is rising in a very rapid fashion, but the supply is slow to respond. Almost, there is a recent study from the World Trade Department that came in, where they did a lot of kind of analysis on what is the expected growth in the global copper demand. This is just one mineral. There are many, many other minerals, and it's roughly about 40%. And then roughly 80 new copper mines that may be needed by 2030, which is almost a $250 billion investment by the end of like 2030. A simple way to kind of visualize the problem is, as you can see, that from the tonnage perspective, what we need and what kind of, we will have, and what's the gap will be there. But what that means for the mining side, what the mining team feels is they have more tons to move with less margin for delays, right? So the more delays, the less margins. Higher energy cost in crushing and grinding, which means you can't just move tons and expect that kind of your same plants and same mills will perform at an optimal rate. More pressure to prove safety and compliance. There is from the regulatory side, there has been a continual focus on how do we improve our safety and compliance. But then the other big challenge is hiring and talent that exists right now, where just to fulfill the critical roles, we don't have enough talent, for this industry. So how do we kind of address that, and where the AI can play a role there? But also understanding why the supply is slow, because mines just takes more time to open up. And a typical mine takes roughly about 16 years from discovery to production. This is almost at an average rate, right? Where considering you have all the approvals and everything is ready and permitting and everything, and then you kickstart the whole production process. But in general, I have seen like 20 to 25 years is the usual rate. And the lead time, which means mine operations to really be productive from construction to kind of, what we call construction to startup to production, that itself has a very ramp up time there. So what we really need, the fastest path, is get more value from the mines we already have, which means already in the production, waste less energy throughout the process, and then reduce the rework. This is usually often happens when you mine a ton, and when you're moving it to process it further, how do we actually optimally improve those outcomes? So which means improving the blasting outcomes, making safety decisions with current existing measurements that you are taking. So this is where practical kind of AI really helps here. But it's important to understand there was a lot of hype that was there about the AI, how when the ChatGPT initially got launched back in about 3 to 4 years ago, and it really became mainstream, there was a lot of promise was there, right? People started to realize that this is the magic button, and it would replace it will bring a lot of autonomy, it will bring a lot of kind of automation, but that did not happen. We were told that it will replace the human factor and it will run mines autonomously, but that did not happen. Almost 60% of these pilot projects failed because it lacked clear ROI. And the reality is, in 2025, it did emerge a lot of reliable tools. We stopped trying to like really replace the human factor, and we started to give them more superpowers, right? What if we can give you more intelligence layer so that you have more information to act on it? So the 40% of this project that survived are now running daily operations. So that's the reality there now. But what really is the bottleneck? The way I see having going through this process in many different applications and the implementations is this integration wall. This disparate data sources and data silos is where a lot of the bottlenecks gets created. So data silos not only kill projects, but really it is the biggest blocker of the AI adoption in any mining operation. So for an example, a smart drill is useless if the crusher doesn't understand where it's coming from, what was the rock hardness that should be correlated to the crusher throughput. LLM hallucinations, we saw that many times, models try to write mine plans but fail basic physics because mining and everything, mining, blasting, and an entire process is built on the core laws of the physics there. And the standalone death, which is if a tool didn't integrate with your existing fleet management system, existing mine planning systems, it would be abandoned, because mining companies cannot just rip the Band-Aid off and get rid of their existing applications that they have and replace with one kind of core AI models. So that will never happen. But how do you actually kind of address these data sources? So you have a standalone systems which currently operates resource planning, mine planning, geology, you have surveying and the IoT data. But then some of them are half integrated, like, planning and the geology might integrate, but then the survey and the other layers of the IoT data will never integrate. But we'll have to move towards more unified platform systems, which means your resource, mine planning, and geology and surveying are talking to each other. As soon as your survey is done, your resource model gets updated, your geology is up to date, and then you have a layer of spatial IoT data from your fleets are constantly updating how it's mined, what's the deviation there. That's where the AI model becomes like a lot more useful, and you'll see start to see some real ROIs there. So the integration wall kind of really started to become more structured later last year, essentially this year, and we start to see some more implementations along the way. Looking at continuing on the integration topic here, we still see big disconnect on the mine to mill, what I call the $1 billion silo. So you have the drill and blast, which is optimized for lower cost with less explosives, but you have mill ops optimizes for throughput, more grinding. But this is just kind of one area we see the biggest opportunity is there, that just 5% improvement in fragmentation can yield 10 to 15% mill throughput improvement. And that's a big shift in terms of how do we take down this integration wall, and then it start to kind of connect different systems, and you'll start to see these improvements then. But let's talk about the state itself, from a bigger picture perspective, where in 2025, where AI moved from trials to daily work, right? So we saw that autonomy is the big focus for a lot of the bigger OEMs, where haulage, autonomous hauling, as well as autonomous sensing in terms of how do we move the tons, continuously got better. Computer vision became a routine for regular measurements. So drones, lidars, any type of kind of survey equipment got more powerful. Phones turned into a field sensor. So your phones are a lot more powerful what it used to be a few years ago. LLMs got more better in understanding the prompt engineering, right? So understanding of the search, summaries, and drafts a lot more got better here. So just in this chart, as you can see, from the OEM's perspective, you are seeing a lot more autonomous trucks being commissioned, almost roughly in the range of thousands now. And this will continue to accelerate in the next coming year in 2026 and 2027. What that means is the application of AI will start to deliver ROI then. So what I see in terms of the silent winners of 2025, which never gets talked about, we only live in the worlds of kind of, if you think about the mainstream, it's all about the LLMs or ChatGPT, or maybe some video models, which can create videos. But these are the areas where it's delivering real value, what I call the computer vision, machine vision, physical AI, and pocket AI. So computer vision is essentially understanding the information from the images, discovering the patterns, and then giving an intelligence layer where it can be turned into a reports, right? So you have drones turning the data into a 3D models. 3D models turns information into a more geometric information. And this information gets utilized on a daily basis. Other example is the 3D camera systems, which can be put on different areas. So now we are really seeing the process optimization from that. The other aspect of the physical AI is, so once you have the data collected from these sensors, either visual sensor or the machine sensor, so once it touches the specific segment of the rock properties, such as drills or crushers, what we saw, it generated more ROI rather than just the pure looking at the software analytics. So combining the physics knowledge of how the rock behaves, along with the sensor information, ROI start to see more better. And then the pocket AI, which the shift from the heavy, ruggedized, bulky scanners that we have seen in the past. Now it has been almost in the trend is you can utilize very powerful device, which is in your pocket, and turn into something more useful information so that you can utilize it anywhere, anytime. Of course, it has certain limitations, but if you can reliably collect some data on a regular basis, so the usability that is the winner here, which means you have more data to play with rather than a specialized sensor or scanner to work with. So talking about two kinds of AI, right? So this is something always a perception that I've had more in terms of how the industry reacts to AI, right? So when we think about AI, it's all about the LLMs. And I touched briefly earlier here that there are more value we are seeing from the physical AI into the mining industry. But I would like to kind of walk through how they solve different problems, but they also fail in different ways, right? So LLMs, large language models, it works with text and symbols. The domain that you have is you have a text, a code, or a document, which means each are stored as essentially the tokens and the context window, and you start to kind of predict the pattern from that, and it is really good at those. And the mechanism is like very probabilistic predictions here. So it acts as more as an assistant. So that's why it feels like when you're talking to ChatGPT, it's sort of like an assistant, right? But it helps you making you kind of giving you more data, more information that you can act on it. But it has limitations. It hallucinates. It is blindly unaware of physical laws like gravity, understanding the rock itself, understanding the geological factors. That's where it has limitations. So mainstream example, as I mentioned, some of the bigger models that you probably are aware of, ChatGPT, Gemini, and Cloud, right? So the LLMs are really good in processing text, but they do not understand rock mechanics. Using them for calculations is a mistake. Now let's put it into contrast with physical AI, which is what Strayos focuses a lot. So we work with sensors, images, spatial data, and machine data, essentially. So the domain is image, point clouds, videos, drill data, sensors, any type of rock inputs. And so it's good at seeing, understanding from that visual aspect, measuring things, building geometrical pattern from that, and predicting outcomes. And then building kind of, also physical correlations, from that. So the mechanism is your computer vision, machine visions, and then a layer of physics engine. So the physics model, the rule of physics that exists in an entire drilling blasting gets incorporated in that process. The outputs are usually tied to the site, which means it continuously needs to calibrate what's the input is given, and it uses that input as a layer to build that information layer from it. The limitation on this physical AI, it requires a lot of calibration, which means you have to continuously train. It doesn't have a self-supervised calibration at the moment, which will require more compute, to do it, and it has weak feedback loops. If there is no human factor behind, the feedback loop doesn't occur automatically here. So the mainstream examples for these models are GPT-4V or NVIDIA, but there is a whole new concept that is emerging now called world models, which means as a human, we develop knowledge by, as we, as a young kid, we start to understand, we perceive things, we see visually, we touch and feel, and then we start to kind of, learn from that. And that's what kind of, this world model is. So you may have seen in the world of like robotics, how the robot sees, but it has to continuously train millions of times to pick up the same object. But as a human, we exactly know because we understand the gravity. Robot still does not understand the gravity. So there is a concept of the world model that has been now emerging now, which can understand and see the physics, and there is an incorporation of the gravity models there. Where the physical AI is very, very useful. So simulation-based training. So if you have a digital twins, which can be utilized for trainings and testing complex physical interactions. For example, rigid body dynamics, any type of lighting conditions is there. You can simulate, for an example, if the camera sensors are at dark environment, what type of information will generate? If we understand the exposure rate more properly, what type of anomalies will come out? The other areas is physics-based learning. So training the AI to understand real-world physics law. So for example, certain characteristics of rock, how the timing correlates with the rock geology and what's the blast movement will be. So those learnings is just not the data patterns, but it is essentially the simulation of the physics itself. Then you have the multimodal integration, which means combining the sensory data, such as visual information along with the touch, and then building this actionable outputs, from that. So typical examples here are the autonomous driving or autonomous hauling that we have seen. That's where multimodal integrations can be very useful. The robotics is one of the fields where the sensory information along with the vision and touch are very much applicable. And we're going to see a lot more advancements in the drones, which is another robot, where the multimodal integration will play a key role now. So LLMs really didn't replace human factor in 2025. What they did help is work around the work. What that means is it helps summarize your shift notes, maintenance logs, draft reports, permitting, checklist faster. What is the spec and procedure kind of, types of questions. For an example, find out information about in the last 5 years of shift reports where the conveyor failure happened, and then correlate with the weather pattern, right? So that's a good use case for the LLMs here. Or summarize the 50-page geotech compliance reports. Let's say you ran a high-vol AI in Strayos and you got 50-page report, but it's still, how do you make it very actionable, that what information that you need to give to a crew on the field where they need to act on it. So that's another good use case for the LLMs, which means scanning and drafting an actionable checklist. So where LLMs are risky in the high stakes environment. So making blast design changes without checks, right? So that's kind of, can't rely on calculations, as I mentioned. Choosing slope controls or exclusion zones based on the LLMs, based on just querying your last kind of, let's say 50 blast reports and say, find me an exclusion zones. That's not a good use case. Writing facts with no citation. This is the big thing that NIST, which is the National Institute of Standard and Testing, that they call out risk and context gaps, that the citations must be needed in each of the AI model output that's been created now, especially for the high stakes environment. Driving control systems, which means integration of the conveyor information and controlling the feed rate from the LLMs. That's not a good use case. That's a high stakes use case as well, which means if the model predicts wrong outputs, you can shut down your conveyor for no good reason. But just quick view of like how it has been trained, this LLM. So you have a lot of kind of corpus of data, and then it's been self-supervised, like training models are built in, including the pre-trained models there. So, and then it gets adapted to as you put questions, and then it then predicts the information, the token, which is essentially, and then it retrieves the information from each token and gives you the output then. So essentially, it's a very much trained model that's giving you the different information that based on the prompts that you're putting. So a safe way to use LLMs on a mine site. So this is something that it can be easily implemented if you start to kind of like really find a use case in your minds, right? So you start with your documents. So you must have a lot of SOPs, operating procedures or manuals that you have created, or a lot of training documents that you have. So what you can do is you can store that, you can build kind of, a memory system, and you can correlate each of these training manuals with a citation, and then you can have like a human sign off who owns the final decisions after you implement this as LLM in your operating site here. So good goals to kind of pursue in your 2026 for implementing LLMs is, for example, what is our vibration limit for this bench? This information, you probably have it on your fingertips from the blasting operations perspective. But if a new trainee comes in and joins the operations, if they search this information, it's there for them as well to review. With last 50 documents that were produced about the vibration limits. Similarly, any type of incident narratives, compliance information that has been produced before, and any type of kind of training, that is another good use case where you can implement LLM. And again, not a good target is direct control of physical operations without any engineering checks here. So let's talk about the physical AI. So physical AI is where most of the mining value are showing up today. And this is based on our experience with having worked in many different implementations with a lot of our kind of great customers that we have. And the feedback that we get is the aspect that they can take this and put it into a site, and they start to see the information. And that's where they can calibrate and predict and have at least a baseline studied faster. This is where the biggest feedback that we are getting. So it's starting with what is happening, right? So if you are not measuring, you're not understanding what exactly going on your site. So what I call perception and measurement. So it's starting with images, point cloud, sensors. It will give you quick fragmentation measurements, high wall, hollow checks, stockpiles, volumes, but then identifying the deviations, the patterns. In fact, you can automate some of these tasks, which usually took longer to just click buttons. Now it is automated, through quick measurements you just run, and then you have reports ready. But then the second layer is the prediction. So you can estimate outcomes such as fragmentation. So you have a lot of historical data, and then you have the new design pattern information. If you can grab that and calibrate the information from the last 10 shots or 20 shots, your prediction models continue to get better than blast movement modeling, air blast, as well as ore routing risk flags, where you can really understand how much the mixing of ore and the waste is happening. And the third is mostly on the control. And this is where really it needs to be more guarded. there needs to be a human factor in the loop, and usually have to set boundaries and limitations how this needs to be implemented, because this is really touching the machines directly. So for an example, autonomous haulage, so you can measure, predict, but after now you have to make a decision and pass a decision to the machines where where the hauling route needs to be for today's shift, second shift, how the hauling operations should carry out. The crusher gap, if you're getting a lot of oversize in the crusher, real-time adjustment of the crusher feed rate, how that impacts. So again, there needs to be a human factor in the loop if you're automating those scenarios through AI. And then alerting and exclusions, which means if you're building an alerting system, how much alert is an effective alert and how much alert is more of a garbage in, garbage out, which means you can build an alert and there's a lot of alerting just goes into a non-factor intelligence, which it doesn't get factored at all, but it is a useful information, but it is giving you so much alerts, you don't consider that as something to act on. So that's why having a human to like really understand where those alertings are useful and then curtailing down those criteria. But really what we see is measuring everything in terms of the dollar values here. So what we saw is in the Gen AI, which is in the LLM size, the efficiency improvement is roughly in the range of $5 million in a typical operations in which are producing 10 million to 12 million tons. But the physical AI, where like really hard costs were measured as an optimal kind of ROI outcomes there. So really physical AI is kind of leading the way where a lot of the implementation has happened in last 2 years. So talking more in detail here. So physical AI is really what we see as the new workhorse. You can understand things about rock, lithology, understand the seam orientation detection before you plan out your blast. But then throw in your measure while drilling data, understand your physical properties of each downhole rock column there, whole column. So you combine the photogrammetry surface data and the measure while drilling data, and then output is not just a text summary here, but you're getting the 3D hardness map, which you can act on to build a specific energy modeling for each whole column now. So this is where, again, it is started to see the real implementation here. The other one is what we see is the intersection where Strayos sits. So what that means is you see things and then you can talk to those physical models. So for an example, when we use physical AI, we understand things, what is rock and what is the different structures are there. And then if you can incorporate the LLMs there, hey, Strayos, highlight all areas on this bench and burden less than 2 meters. But then it gives you information that there is a dominant joint also sitting there. How do you load that hole? So these are the areas we see a lot more prevalent now. In the future, it will continue to become more normal here. The other application is what we see, the physical AI looking at in this image, the conditions of the material movement, where it is getting thick, where it is getting more runny. But what that really means in terms of the chemical injection, that how to maintain a specific texture of the conveyor belt. And that's what where the AI is guiding how much chemical is needed now. So this is another area we see the physical AI quickly proves the use case in the operating plants here now. The other areas that we saw a big uplift in 2025 was we call pocket AI. What really enabled this is the computing power in phones. So also we were able to compress our AI models into a lightweight models. So the field teams can utilize this tool where they can take quick measurements, and then you start to carry like heavy gears, right? You have your own phones, you can capture daily information, and anybody can do it. So spot checks becomes a lot more common. instead of sitting on instead of sitting days to have someone come in and do those kind of surveys. So why it matters? If the measurement is easy, your feedback loop gets tighter. And that's what kind of the entire focus of this team is, like, how do you break down the integration wall? And that's where the most of the improvement comes in. More data, more information, connecting everything together. And the drill and blast is the leverage point here. So, the fragmentation shapes loading, throughput, and mill energy. About half of mine site energy can sit in communication. So it depends on site to site. A smaller site, which is producing less tons, will have a different energy factor, while the bigger, mine sites, they could spend a lot more on just the crushing and grinding there. So small improvements matter depending upon kind of, different stages of the site itself. One blast affects many downstream outcomes here. So, for example, dig rate, bucket fill, crusher blockage. We have seen a lot on this specific segment where crusher blockage and oversize handling was the key driver for the physical AI implementation. Really trying to understand where things are being choked, understanding the sag mill throughput, right, and then understanding the circulating the load better. Energy per ton in grinding side, which means if how can we reduce even just 1% of the energy in the grinding, which is a huge uplift and just a cost saving side. But it all start to happens from the drill and blast, where you start to measure things and give a feedback to the mill side. Looking at how the physical AI will continue to drive the implementations, we see a sensor fusion gets a lot more robust in the 2025. It will continue to get more strong in 2026 and the coming years. And the reason is the sensors are becoming more cost effective, and then the mindsets are also started to understand the data and the ROI better now. Previously, it was just a cool tech. Now they have started to leverage the data to start doing the baselines. So we're going to see a lot more adoption of the physical AI in the future, because your drill data, 3D geometry, and post-blast outcomes are in one place now. This is the biggest factor that drove this implementation. So you have as-built bench, you have drilling sensors, you have design pattern loading and timing, and then you have measuring outcomes, which is fragmentation and blast movement. And then you have the prediction models as well in one place, which is continuously calibrating. So it start to kind of drive this implementation process, which was not there before. What if we can understand the poor burden and then the irregular geometry that got created from that blast? So now we have backbreak information, from that. How do we target, understand the hard and soft zones from the drilling signals, which is the MWD data, but then what it got correlated to the crusher throughput. So if we can correlate the specific rock hardness zone to the crusher throughput, that's where, again, the physical AI is creating the real impact there. Adjusting loading and timing, as we had talked about, including the fragmentation and feeding it back to your blast models. So Strayos is doing a lot of work on this specific segment to tie things together from design to measure here. But what real measurements kind of looks like, measure outcomes every blast. We have seen this, and then we've seen this from how we can measure things at the blast, how the prediction models use this information from prior shots to improve it, how the blast movement can be utilized to understand throw distance, trough drop, and different kind of stripping ratios properly, how it can be utilized to tune the designs to understand the oversize, reduce oversize, and any type of choke points are there. And then including what that means for the vibration as well. If you can throw in all the historical seismograph data for that specific site, start to build a model where the optimal PPV it will be there for a specific timing. So fewer surprises at the crusher, throughput, tighter control for your environmental aspects, and better learning over time. That's where the real impact is there from physical AI. We look at kind of, from trial and error to physics-based certainty. So for the last 2 years, especially, I would say, we have started to see bunch of implementation focusing in this specific, the whole process, which means you have a data that you have done from the survey. It measures different criteria, understands the rock hardness, understands the geology, and then you historically put some data, and then you start to build simulation, and then you predict things there. So what it used to be just one general trial and error based certainty. Now it became kind of more physical AI is driving more predictions, which getting a lot more closer to what the actual outcome might be there. So another application we saw is the ore dilution control. So usually this is the big problem that happens in the metal mines. You have waste boundaries that doesn't get picked up more effectively, and then you start to see a lot more dilution problems in those sites. So you have shifting ore boundaries, digging ore polygons that sent to the dump areas while it's supposed to be sent to the actual mill, and an entire process gets disturbed throughout this dilution control process. So you in fact you start to focus a lot more on where the problems are instead of the continuous improvement then. So the physical AI, where we see biggest improvements on this area as well, is it can track 3D movement, combining the actual physics model along with the drone scan data, along with your resource model to predict the actual ore polygons and the dig lines there. So what we saw is the site see the 5 to 10% reduction in dilution, which is contributing directly to the improvement of the mill grade there. And we have seen this implemented as one of our customer site, where we are seeing almost roughly an oversized material reduction based on the optimal burden and spacing based on the prediction, the tool that they were using, which resulted into less crushing energy as well, roughly up to 12%. So I want to point out LLM cannot do that because it requires really understanding of the spatial information. So the spatial information combines the geometry, geotechnical information, and the any type of geology information there, along with your design information. So having that specific information is required for prediction accuracy. The other aspect of the physical AI we have seen is at the plant itself. So see the ore in real time. So it means if the plant see the feed changes very early, it can adjust faster the downstream. And the typical examples here are the ore size analysis, also the chemistry analysis as well, which is a big factor with the hyperspectral sensors now. So capturing the ore data at the truck point, the crusher, dump, or at the belt will allow you to make those changes. But then also the process teams. This is one of the big area. If I can understand continuously my reduction ratio, how I am reducing my fragmentation, I can adjust my model, my model of how my end product gets produced. So if I really have this information close to real time, I can really adopt different conditions for the plant. So helps avoid the crusher jams, but also the feed variability that you are seeing. You can adjust those like more proactively here. And then we saw a lot more implementations on this side as well, where they started to correlate the plant data to blast outcomes that they have in the customer location, and they start to like really understand how do we make the different changes in the blasting side. The other aspect of the physical AI is more on the digital twin side. So what if you can continue to measure and understand how the mines are being developed and what's the different aspects that you need to measure. So for example, after every blast, how the high-level compliance is there, easily understanding the reconciliation. Haul road checks different conditions, grades, potholes, measuring different safety compliance. So it's building this digital twin, and this digital twin gets updated real time. If not real time, at least you're updating every week. Now you have the plethora of information to understand how my mine plan is faring up with the actual as built now. So whether we are going in a right direction, whether we are going in whether we are going the direction that is not desirable there. The other aspect is like really understanding where the trucks are moving the material from. So this example in the third video here, it like really correlates where the different blasts have occurred and how those materials are moved to the crusher dump point, where the camera is correlating which blast is performing what's the crusher throughput correlated to that blast. So a real 2025 pattern that we're going to see emerging, as well as we're going to see this continuing in 2026, is the adoption of, or the combination of digital twins plus the LLMs, for your decision support here. And then one example that I can clearly see emerging at our end is if we can combine the digital twin with the LLMs, you're going to start to test more scenarios faster. For an example, this is where the information of the blast is being measured at the plant. If we can integrate the LLM as a decision, or at least at the questioning layer, where you can model different scenarios faster. So that's where we're going to start to see like really good understanding of planning decisions. Which blast is giving me better blending, which blast is giving me better throughput, and what changes that can really require there. So the simple model that I see is you have the LLM layer, which is the language, and then digital twin, which is more getting up to date from your surveys, and then also the information layer that you're putting, design and the prediction, and then the measurements, which is being carried on a daily basis or a weekly basis. So all this combined together will start to build this kind of decision support layer. So the key takeaway is really you have the LLM, which sits on the top, but the core information comes from the physical AI there, where the twin and the sensors are the truth layer, what I call the ground. It's not exactly the full ground truth, but it is updating that ground truth information more consistently. So if measurements are weak, also the language layer cannot save you. So this two layer is very much of an importance for your LLM integration to work. So the biggest reason we saw AI project stalled in 2025, because as I mentioned in the integration wall was the issue. So we talked about how it was the platforms were structured, but then if you start to combine the geology, survey, drill, and blast, start to kind of build that feedback loop. If there is a no feedback loop, you will see start to those information just becomes as a measurement, not becomes as more the AI feedback loop there. So how do we fix it before 2026? We still have a couple of weeks left, but I'd start to give you some time to think as you enter into 2026, how to pick one thing to start this implementation process. So pick one loop, right? So from the blasting to maybe just as a crusher throughput understanding, and agree on a shared data set. So what data that we want to apply and start to measure, and then automate this information gathering process, and make at least like, create a team around it, or at least dedicate one person to understand this metric. Because if there is no one accountable to review the metric, the AI projects will continue to get stalled. Autonomous mine is one of the things that has been talked about from last, I would say last like 8 or 9 years or even 10 years. but it is continue to be the buzzword still. And the reason is because it is still a closed loop in terms of where the open autonomy that we talked about, that the different equipments, different machines needs to start sharing data more effectively. Once it happens, we'll start to see more implementation. And we'll start to see more at a software layer, but it's still at the equipment layer. This data needs to be more calibrated often. For example, measure while drilling data is not as useful just by itself. It requires a lot of calibration. It requires a lot of filtering and parsing there. So we start to see this standardization coming into 2026 on these specific factors now. The other examples that I can pick is we'll still have a gap on how the plant operations, which is machines in those segments, how they feed the data, and what that needs to be standardized. So until that is standardized, the case of autonomous mine will not be a reality there. So there's a lot of work to be done, but it is going in the right direction now. So one thing that I would like to propose, or at least talk about, is each of these loop requires a KPI, a cadence, and an owner, and a single place to kind of store this information. That's what model can learn from. Until that is done, all these AI projects will continue to be more delivering the one single ROI rather than looking at the holistic autonomous mine ROI. So with that, I would like to kind of focus more on what Strayos is doing in this regard, is connecting geology, design, and performance data. And our goal is simple: helps teams see what has changed, why it's changed, and then what to adjust next. Right. So the dashboards, where it brings all the information very effectively in one place, you can find the trend and then understand the operational KPIs. If my burden and design information along with the rock hardness is resulting into an oversize, I can quickly spot check that and then compare across the blast. Scenario modeling, if you can understand what the different parameters of my blasting is resulting into what type of oversize or the fines, whether chemical crushing and mechanical crushing, where the dollar leakages are. So understanding those what ifs. And then the operations optimizer, which means choose among known options. You have a best combination of design choices and then also historical data to refer to. What I call assistant meets operator, so which means you have, we talked about, using LLMs as an assistant, but physical AI kind of more as an operator. And if you can combine both, so if I'm a user, I will ask, show me the blast data from Tuesday with a poor fragmentation. System pulls up the 3D model, highlights the fault line or fracture data along that, and overlays the MWD data. And then now you have a clear information, or what we call the physical twin, to see like this is the pinpointed information, and that's what the poor fragmentation can be correlated to. Maybe not perfect, but now what the information can do for you now. So mine-to-mill works best when you have the same team, or when I say same team, when you have a geology, you have drill and blast team, when you have a plant team coming together to see the same information. This is the biggest problem in how we are structured in terms of the implementation, where a mine geology team is different. They have a different type of information. They are working on a block model or the ore control, but they don't have a full blast information. And this is our goal, to kind of bring everything together and make kind of physical AI more relevant there. But then also bringing the plant team. What was the impact of the crusher throughput from that specific blast? That is the information that plant manager wants to know. So how do we talk about the next phase, right? So the next phase is language on top of the measurements. You have a decision layer, you have a physical AI, and then you have a LLM layer. And then you start to kind of build this kind of model where it sits on a lot of data, but also it sits on the decision layer then. And you start to see some real ROI based on the baseline that you have created, as well as the new information that's coming out from the model. So 3 actions you can take for 2026, like pick one closed loop model, which means, let's say if your goal is to reduce the oversize, if your goal is to reduce the fines that you're generating, or if your goal is to avoid the back breaks or improve the floor control, pick one KPI and then make measurements continuously and consistently for that specific KPI. And then have that dedicated KPI reviewer, which will assign that next phase of decision making there. So that's what I would encourage everyone in this call to think about as you're going into the 2026. With that, I will end the webinar here, and we'll take some questions.
Thank you very much, Ravi, for that informative webinar. It was very informative and helpful. We don't have any questions in the Q&A bar, but we were sent a couple questions ahead of time via email. The first question would be, can you discuss the differences between how LLMs and Strayos's computer vision are trained and work?
Yes. So LLMs are trained on a corpus of data that existed on the internet, right? So you talk about any social feed or any lots of books were there, as well as the Wikipedia. So anything that's related to the text were utilized to build this LLMs, and it is continuously evolving. Strayos models, we predominantly focus on the computer vision, machine vision. So it takes the data such as images, LiDAR sensor, or any other information where you can build information from the pixels, right? So images, videos, LiDAR, and then we structure that information to find pattern. So the typical difference in the models are these are all visual models, which means it utilizes the convolutional neural networks, which is really trained to identify different aspects and the pattern recognition there.
Thank you. Let's see. Can you explain why Strayos isn't subject to some of the problems that LLMs have, such as bias, hallucinations, and sycophancy? Sycophancy when the ChatGPT agent tells you how wonderful you are all the time and how great everything you do is.
So I think what I call the hallucinations does exist. It's more in terms of the predicting the wrong things from the visual perspective. If, for example, if there's a haul road and it has predicted a berm, which is not necessarily a full berm, but there is a pile of rock on the side of the road. So those things does exist, what we call the model anomalies or the false positives. In that case, we go and retrain those false positives. So there is a continuous iterations there. The another example is in terms of the rock detections. So if there is a lot more bias coming in the size detection, you have you go and retrain again those size detection models. In comparison with the LLMs, how I think I'm forgetting the question now. So you have the bias. So the LLMs are biased not because it is giving you the wrong information, because It's how it is like trained. It's because it is limiting certain set of knowledge. And that's where it may feel like it is biased, but it is essentially resulting into a limited set of information where the model is limited.
Okay, a couple questions from our guests today. Where does the design, measure, learn loop break most often in live operations, and why?
So the design learn loop, really what we have seen is it works consistently well, at the one department phase, which means if you have a blasting department or geology, they may update the rock model there, but then what's going into the mill side, this is where the biggest disconnect happens. You don't have that layer of information readily available until you start to put a process and start to measure things more, effectively. And that is kind of one of the areas that we are really doing a lot of work. How do we build the sensor layer of data collection so that this collection of data becomes a lot more easier? So this is where we see a lot more gaps there from the learning part.
Okay. Could you please answer what failed more often in AI projects? The models, the data quality, or the operating model?
So in our experience, what we have seen is a whole lot related to the data quality. If the data is not good at the very first level, the model fails. And also it can be because we can train the synthetic data to find out the data which are bad, but it has not reached to that level yet. So the data quality is definitely one of the key factors where the models underperform. Then the other aspect of the model non-performance is really this models has gone through continuous iteration process, and it does require teaching them continuously. And the teaching also requires calibration of the models. And if the calibration is not happening from the user input side, that's where the model will stay stagnant, and it will not continue to improve. So the user input is really another driving factor there, along with the model training, which is from the AI engineer's perspective who trains.
Okay. How concerned should we be that the AI will go rogue and destroy humanity?
Oh, I think that, I don't know if this is a question from the audience or if this is just now. For now, I think we are at this stage, we are finding basic use cases. So I'm not even worried about that.
We have a question. I'm going to read it, but I think I'm going to field it real quick. Please elaborate more on the use of photographic data in 3D models. That is a very big question, and we could spend many hours discussing how photographic data is used to create the 3D models, and we actually have in other webinars. So I would be happy to share links to those other webinars and some materials on how that works, just because that is an entire topic all on its own, and we really don't have the time to address it here today, but I am happy to send you that material. What is general AI?
So I think if I understand the question properly, I think it might be referred to as a general artificial intelligence, which essentially creating one model that has answers to everything. That is what the general intelligence is, which reaches the level of the human intelligence. I think we are far too away from that. We're still solving world models, which is kind of understanding, teaching the physics, right? Which is requires a lot of compute and training. We are not at that stage, having the general intelligence.
Okay, that's all of our questions here today.
Great. Well, thank you, everyone, for joining in today. I know we ran over time here, but really appreciate sticking around, and hope as you enter into 2026, you see the different technologies coming together, what physical AI is, what LLMs is. It gives you some framework what to kind of think about. So I enjoyed the session, and we look forward to continue doing it for the next year. But until then, happy holidays to you all. We'll see you next year. Bye-bye.
Thank you, Ravi.